Okay, so some of you guys have come to office hours to ask questions about your group project, which is very good, and it seems like my interactions with the group has been encouraging because it shows that people have been asking good questions about their data and have been encountering some problems or just encountering some issues that require some thinking. And that's always a good sign that students are thinking about their data. And so, if you haven't visited and if you have questions, don't hesitate to come by. I'll do my best to try to guide and give you some counsel there. And I know a lot of students are concerned about the modeling section because you're not quite sure what you can predict or things like that. And I just want to say you don't necessarily have to make predictions, okay? So, in some cases your data sets might have a thing that is like a natural thing to predict, such as I don't know, there's some numeric output and you want to try to predict whatever that numeric output is, okay? Or there's a classification and you want to try to predict that. And that's fine. And and for the modeling section is not going to be graded on accuracy or performance or anything like that, okay? It's going to be graded on just kind of thoughtfulness and appropriateness, okay? And so in some cases, it makes sense to make a prediction, and I want you to evaluate how well your model makes predictions. And even if your model doesn't do a great job of predicting, that's also okay. And then on the other hand, I don't want everybody to feel like they have to make predictions, okay? So the other option I wrote was for like insight, okay? And insight is more so exploring relationships between the variables, okay? And this is probably, related to the exploratory data analysis, but it could come down to, maybe you're clustering some observations together, or you do like some kind of dimension reduction, or you find out that certain variables are kind of redundant, or whatever it might be. Insight could be something where you find something interesting and you're not necessarily trying to make a, quote, prediction, okay? If you think back to, like, if you participated in Data Fest, a lot of times there wasn't, I think every Data Fest, there wasn't exactly something for you to predict, okay? They wanted to ask, what is the relationship? What variables are related to fatigue, or what variables are related to this and that, okay? That all qualifies as like coming up with a model for insight, not necessarily something where you're making a prediction, okay? And I know a lot of these tools that we're learning with sklearn and these machine learning things, a lot of them do make predictions. You make a model and you do have a prediction, but I don't feel like, I don't want you to feel like you have to make a prediction, and I'm content with some kind of thing where you're creating some kind of insight or relationship, kind of, I guess, backed up by some kind of slightly statistical test, okay? So if you're not making a prediction, but you want to see, is there really a relationship between these two variables? Okay, if it's categorical, you can do like a chi-squared test. If it's numeric, you can look at, correlation for a linear relationship, or something else to see if some kind of relationship exists and things like that. So anyway, that's what we've got. As far as today's lecture content, I just thought we would take a look at a few more things in sklearn. And, this first part will look a little bit more into cross-validation with sklearn. And then I'll just shamelessly copy or we'll take a look at some of these models that's part of sklearn in the Python for Data Science Handbook, okay? But first we'll take a look at cross-validation, okay? So I'm going to start by importing NumPy, Pandas, and Matplotlib, and then from sklearn, here, let me say, restart and clear all. And then from sklearn, I'm going to import pre-processing and model selection, some of these functionality. Okay, so go ahead and import these modules, and then I'm going to take a look at this iron slag data. Okay, so this is this data set where they were trying to figure out kind of the iron content of some kind of metal alloy that is from some manufacturing process. And apparently, in order to figure out the iron content, the true method requires a chemical test, but it's a little bit more costly, and you can do a cheaper test, which is a magnetic test, and it reports back similar numbers, okay? And so I guess it's kind of like, I don't know, at home you could measure, I don't know, you might have a watch that measures your pulse, and maybe it's super accurate, I don't know, versus like going to the doctor's office and they measure your pulse there. Actually, pulse is probably going to be accurate in most of these cases, but it's like something at home versus going to the doctor, right? And so they have a chemical test, which is more expensive and more accurate, a magnetic test, which is cheaper but maybe less accurate, and we just are exploring the relationship here. Okay, so we'll make a scatter plot. This is what it looks like, and they're positively correlated, which is a good sign. The question is it a linear relationship? Is it something else, right? So one thing we can do, all right, is we could just fit a linear model here, okay? And so if we look at iron, this is kind of what the data set looks like. We're going to take X and we'll use kind of the chemical column as X, and we're going to try to predict magnetic. And so we're going to take the iron chemical column, the values in that column, and then we're going to reshape it to be one column. This reshape -1 is basically fill in the rest, right? So what normally with reshape, if we want to make a matrix out of it, we would need to specify how many rows and how many columns, right? And so here, I don't know the exact dimensions, but I would need to figure out the number of rows, and then I would say I want one column. But because I'm a little bit lazy and I don't want to actually figure out the number of rows, I could just do -1 here, and then this will tell Pandas to reshape it and fill in the number of rows. So if there's like 100 rows, it's going to reshape it to be 100 by 1. So this is basically question mark by 1, and we get that, and when it does that, it says, okay, I reshaped it to be 53 by 1, okay? And I didn't actually have to specify 53 by 1 here. Okay, Y will be basically the magnetic column, which will be just 53 values, okay? And the thing is that the reason why I had to reshape this was that sklearn requires that our sklearn requires that our X has 2 dimensions and that our Y has only 1 dimension. So it's important. So I couldn't just do I couldn't just do chemical.values, which would be 53 comma. I needed it to be 53 comma 1, right? So anyway, we can calculate the correlation coefficient, okay? And this will give me an R² value, okay? So correlation, and if I square that, star 2 gives me R², right? Okay, so if we do sklearn, we'll just do linear model.linear regression. And then, so that defines the model, then you do model.fit, okay? And that creates that fits the model. And inside the model, technically there's like an intercept and a coefficient and this and that, okay? But sklearn isn't about like returning these coefficients. So generally in R, when you fit a linear model, like immediately it tells you back, here's the slope and here's the intercept, okay? But sklearn is a little bit less into like giving you back the coefficients, and it's a little bit more like, these are how the predictions we get, okay? And so here we can ask, you know, how good is this model? You can ask for the score, and you give it the X and Y data, and it gives us 0.537228, which is exactly our R-squared value. So the score is the R-squared value. You can ask, you know, can you make a prediction for the values from 10 to 33? Okay, and again, we have to reshape it to be some kind of matrix. So we do that, and then we ask for predictions, and then we can kind of plot this, and we get this straight line here. Okay. So here it made the predictions from 10 to 33, and it draws the line, and this is the fit that we get. So that's just straight linear regression. I think we've seen that before. If we wanted to do cross-validation, there's a few things we can do, okay? So one is we can run shuffle split, which says, you know, create these kind of cross-validation blocks. And so take our entire data and make 5 splits. Okay, and our test size will be around, you know, kind of 30%. Okay, and I initialize it with some kind of random state so that it's reproducible, right? And then so once I've specified how the cross-validation is done, I can run this thing called cross-val score using the linear model that I created back here, okay? So I've created this linear model, okay, linear model.linear regression, and I already fit it to the data, but we ask for the cross-val score of this model that I've created using kind of the full X and the full Y, but we tell it, I've split the data, I've created these partitions using cross-validation, okay? And so what this is going to do, when you ask for CV linear, it's going to spit back 5 values, okay? And these are the cross-validations for each of those. This is the linear model score for each of those 5 cross-validations. And the overall mean cross-validation score is only 0.46, okay? So when we had the full training data, our R-squared value is around 0.537. And if we look at our cross-validation scores, in some cases, I get R-squared values like 0.75. Over here, I get an R-squared of around 0.49, 0.65, 0.412. But here, I got an R-squared value that's actually negative, okay? Which seems bizarre. Like, how can you get a negative R-squared value, okay? Does anybody know how you can get a negative R-squared value? Does that even make sense? It actually does, all right? So if you think back to linear regression, how does, what is SS total? It's the total sum of squares, but how are you calculating SS total?
Predicted minus the actual value.
Okay. All right. Let's see. Okay. So let me draw this out. No, cancel. Let's make a new thing. All right. So the idea is you've got something like this. You've got some points here, right? And then you've got SS model, SS error, and SS total. Okay, and then so the SS total, this is based off of, you're going to calculate the mean. This is like your y bar, and it's the difference of basically each point minus y bar squared, the sum of these things, right? And then SS model is going to be something like this, right? And then your residuals, I don't know, are like this, okay? And so the SS error is it's the sum of basically y minus y hat squared, okay? And then the SS model is y hat minus y bar squared times n, right? Well, I guess it can just be this also. Is that all right? So this is how it goes. And usually, generally, you'll have this quantity plus this quantity is equal to this quantity. Okay? So this is, what is this? This is RSS, and this is SST. And what's this part called? No, if this is not... Okay, well anyway, I forget. I don't know the letters. Huh?
SSR, SSD, SST.
Oh, it's SSR. SSR is the model. Okay. All right, so sorry, I got that wrong. But basically your R squared is going to be SSR. RSS? Sum of scores regression. That's what it stands for. I can never remember these letters, all right? All right, SSR divided by SST, right? That's what it should be. Or it's also R squared is equal to SST minus SSE divided by SST. This is what we've got. Okay, however, what if what if we have this? So you got something like this, okay? So this is y bar, right? And this we still have SS model, and then SS error, and then SS total. Okay? So SS total is based off of y minus y bar squared, okay? But what if the fitted line is like this? This is your y hat, okay? If you look at this, all right, the errors, these errors are like way bigger than the errors to just y bar. Okay, so if you look at SS total, it's kind of these things, whereas now the model actually does a worse job than SS total. Does that make sense? So the prediction line does worse than y bar, okay? Because that's what we've got. So this SS model, this is actually larger than sum of y minus y bar, okay? So so SS model is still y minus y hat squared. So you still have that relationship, but it's bigger than this. Okay, so if we have SS model plus SS error is equal to SS total, SS error ends up being a negative value. Or did I do it backwards? I'm sorry, I have this backwards. The SS error, sorry. The SS, yeah, I'm sorry. Too excited. So I'm sorry, the SS error is bigger than the SS total. That's what I should be saying, okay? Okay, so the SS error is still y minus y hat, and then the SS model, this part, ends up being negative. Okay, does that make sense now? Did I still make a mistake?
So that error should, so SS model should be the second line, right? So the error.
So,
Oh
yeah, SS error is y minus y hat quantity squared, right? That's your residual sum of squares. And what we're seeing is that because this prediction line is so bad, like the SS error ends up being bigger than the SS total. Okay, and in order for the SS model and the SS error to add up to SS total, SS model actually has to be a negative value. Okay, so that's how we get a negative score on SS model. Is that all right? Okay, and so technically this is all we need to do, but to kind of illustrate what's happening here, I wrote a bunch of code. And so basically, we've created our cross-validation splits here using shuffle split. And technically, I'm going to do cv.splitx, and it's going to split x into, some training indexes and test indexes. And so now I've got my tx and ty for my training x and training y, and I just basically subset my x and y accordingly. And then I'm going to fit a linear regression model to the training x and the training y. And then I get out my test x and my test y, okay? And then I'm going to plot all of this, okay? I plot my training data in blue, light blue, and I'll plot my test data in green, okay? And then to get kind of my scores, so actually this will be the predicted line on the training data will be in red, and then we're going to have just kind of the mean value, kind of the baseline for SS total, that will be a light green line. And then we're going to just ask, kind of the baseline is just the variance test-wise. So if we, in this, whoops, SS total, SS total is kind of variance before we divide by n-1. So that's SS total. And so what I do is I'm going to take kind of the mean squares, which is going to be the difference between y and its predictions. We square that, and we divide by how many we have, and we just do the difference in the MSE, okay? So anyway, when we plot all of this, this is what we get, all right? And so, so the red line is fit on the light blue dots, okay? And our test cases are these green dots, okay? And if we see, what's the error? If you look only at the green dots, it turns out that this flat green line does a better job, has less total error than the red dot, than the red line, okay? And so we end up getting a negative R-squared value here, okay? Over here, if you look only at the green dots, then yes, the red line does a better job than the flat green line, okay? And that makes sense because looking at it, you've got positive overall correlation. But here, if you're looking only at the green dots, so ignore the blue dots, but if you look only at the green dots, the flat line actually does a better job than the red line, okay? So here the red line does better. Here the red line does a lot better, and so we get quite a positive 0.756. Here the red line does better, and so we get 0.65. And here the red line does also better, and we get 0.412. But those are where all of these values that we came up with, the negative 0.0086 and the 0.493 and the 0.756, all of these values are based on our cross-validation splits. Negative 0.0086, the 0.4932, and the 0.756, and so on and so forth, okay? And then kind of when we average all of these, we get a cross-validation score. And this can be kind of extended for higher order polynomials, okay? So here I do the same thing. In order to make, we only have one predictor in order to kind of make polynomial regression. You can use this function called preprocessing polynomial features, and 2 will do a quadratic based thing. And then so here we're now going to we're going to transform our x, okay, to quadratic features. And then and now I'm going to fit linear regression to my transformed x, okay? And when you do polynomial features, it generally automatically fits an intercept, so I'm going to tell it don't fit an intercept, right? And then here, we'll do fit poly x to the y, and then we ask for the score, and it gives me 0.593, and then we can just kind of look at the scatter plot on how it fit on all the data, and we'll say, okay, that looks pretty good, okay? And then we can do, again, cross-validation score using this polynomial regression that we've defined back here, okay? Applying it to the polynomial x and y, using the same cross-validation splits, and we get an overall cross-validation score of around 0.50, okay? Which is a little bit better than my mean cross-validation score of 0.46, okay? So it's a little bit better here. So this is, again, fit on all the data, and then when we do the cross-validation, we get 0.503, okay? If we want the similar plots of the breakdown of each thing, I wrote a function, okay, because I saw that I was going to do this over and over and over again. So I wrote poly cross-validation, and I wrote a function that's going to take in some degree the x and the y and the training index and the training test index stuff, okay? And it basically does the exact same thing that we did before, and it's going to kind of plot all of these things. And again, the red line is fit on the blue points, and it turns out the red line doesn't do a much better job of predicting the green dots than the green line. So we actually get a negative value here again, okay? And if you look at it, yeah, there's quite a bit of error between the red and the green dots here, right? Like, yeah, the green line actually does a decent job. But as far as the other things go, it does a pretty good job, especially this one, it does pretty good, okay, 0.799. This one also does pretty good, and that one does fairly decent as well, okay? And then so, we can do the same kind of thing for cubic fits, and our overall score for the entire training data is 0.598, but again, the question is, what if we did cross-validation, okay? And the cross-validation score goes down to 0.455, okay? And we know that as you increase the number of the degree of your polynomial fit, you can generally get higher R-squared values because you've got more predictors and you might be overfitting your data. Okay, and so that's where cross-validation is helpful in helping us detect whether we overfit our data. Okay, and because I wrote the that function earlier, this is we can run it, and we can see, you know, in some of these cases, its predictions. Okay, because again, it's fit on the blue points, all right, which is a little bit different each time. We get something different. Okay, and so just kind of. You know, for a 4th degree polynomial, our cross-validation score drops quite a bit down to 0.218, right? And we can see that we're getting quite a, like, again, the 4th order polynomials fit on the blue dots, and we can see it does a poor job on these green dots, okay? Same thing here. It's fit on the blue dots, but it does a poor job on the green dots in our test case. And so our cross-validation score is low, okay? And here my cross-validation score is really bad at negative 1.35 because this one has an absurdly low score of negative 5.73, okay? And we can see what happens, okay? So looking at this, so for this one, again, the 5th order polynomial is fit on the blue dots. And when we ask it to make predictions on the green dots, it's predicting something way out here, which is really bad, okay? Because we overfit our data. And so, so it is far worse than just predicting the green line, and that's why we get this negative number here, right? So the green line has kind of a MSE of 52, and then if you look at the MSE of this red line, we get 350, and so that's basically 5 times worse. Okay. So anyway, that's what we have in it. And if I did anything, if I just redid this whole thing, and if I put in like a 15th order polynomial, we get this terrible negative 48. Okay, and again, it's fit on the. No, this is what's going on. 15th. Okay, so you get this, you know, really wiggly line, which just does a bad job. And actually, when I'm plotting it, I don't even have enough. Like, look at this. This is terrible, right? So it does a really bad job. Okay, and that's why, you know, our cross-validation score ends up being something absurd, like negative 48. So anyway. So that's that. Again, you probably wouldn't actually bother looking at the cross-validation sets directly, and you would just call this function CV score, or cross-val score, okay? So you can create your cross-validation splits using something like shuffle split, and then you can do ask for a cross-validation score, and it will give you one score for each fold in your cross-validation. So if you have like, so here I did 5-fold cross-validation, but you could have done 10-fold cross-validation, and you would have gotten 10 cross-validation scores, and then you just average those 10 together to get kind of an overall cross-validation score. Okay. And anyway, I talk about this because this is our sklearn's primary method of model selection. It does not do your traditional look at p-values and standard errors of coefficients. Okay. Here I'm literally just copying and pasting code out of the GitHub for the textbook. Okay, so I don't know if you have starred this set of data science notebooks on GitHub, but you can always look up GitHub Python Data Science Handbook. Okay, this is one of the textbooks that we use for the class, and the number 1 hit will be this. Okay, Jake Vanderplas's Python Data Science Handbook. Okay, this is our textbook that we use, and he's basically put all of the code that appears in his textbook into notebooks here, okay? And the first few chapters are on things like NumPy and Pandas and Matplotlib, but then chapter 5 is all on sklearn and different things. And so, and he's got little examples for each of these things. And I think these are very helpful, especially if you use them in conjunction with the sklearn documentation, okay? So, so those are kind of the two things that you should be using, or I mean, the sklearn documentation should be the #1 resource that you're using, okay? But if you want to see like an example of it being applied, this is a great resource, okay? So anyway, we'll take a look at his naive Bayes usage here, okay? And he gives a little bit of background information about naive Bayes. And so, so I'm just running his code here, okay, which starts by just kind of importing our libraries, our modules, and then for our training data, we use just this function called make blobs, okay, which is actually it's a very handy and convenient thing, okay? So you just kind of say, I want 2 centers and random states, and you just kind of give it a few arguments here, and it makes kind of 2 blobs here, right? And again, you can always look at sklearn make blobs. Oops. And it just talks about, so here, 100 samples, 2 features, and that allows me to plot it on an XY plane, and then centers, you know, you give it all of this stuff, okay? So make blobs does this, all right, and so this is what we have, and we're going to fit a naive Bayes classifier here, okay? And so this is, it's very simple. All we do is we just say, all right, import Gaussian naive Bayes. So Gaussian naive Bayes fits basically a multivariate Gaussian thing, except there's no covariance. So the kind of the perimeters or the axes of the fitted models will be perpendicular to each other. Okay, so you've got this kind of this ellipse here and this ellipse here. Okay, if you were not doing naive Gaussian Bayes, I'm sorry, naive Bayes, then you might have covariance, and your ellipse could look like an angle, right? And so we've seen some multivariate Gaussians with covariance, but naive Bayes doesn't allow that. And it's basically, you know, just a product of Gaussian things, okay? So anyway, we just say model is Gaussian naive Bayes, and then we fit it between X and Y, okay? Which is what make blobs does. So if you use like make blobs from sklearn, it automatically unpacks it into X and Y for you, which is quite easy, right? And we just plotted X feature 0 and feature 1, okay, for our 2 features, and then the color is based on the Y's, and that's what we've got, okay? So anyway, you fit it, and then the model is fit, and so to kind of see how well our thing does, here we're going to generate a whole bunch of values, about 2,000 values, okay? We're going to generate 2,000 values, okay? RNG rand 2000, okay? What this is going to do is it's going to generate 2,000 values in kind of 2 dimensions here. And here we multiply it by this to kind of get our appropriate scaling here, okay? And so this is going to just create a grid of points, basically going from -6 to 8, okay? So -6, and then from -14 to around 6, okay? So it's going to just plot a whole bunch of points, 2,000 of them, and then and it's going to make predictions, okay? And as far as predictions go, it's either going to predict class 1 or class 2 using this, okay? And then, so that's it. It's done. So we just generated a whole bunch of points here, and if I just did like y new like the first 10, okay, you can see it. I guess class 1 or class 0. Okay, you can see how it's predicted. And what we're going to do is we're just going to plot the original data, and then we're going to add the new data, okay, colored by the new predictions, okay, and then we turn the transparency on this very low, okay. And so when we do that, you see the original data, and then you kind of get to see, like, so here's 2,000 just random points all around, and you can kind of see where some of the points are classified as red and the other points are classified as blue. And so you get kind of this, some kind of boundary that's appearing between the two. This isn't even necessary, right? You fit the naive Gaussian Bayes. All you have to do is just ask for a prediction for new points, okay? But here we gave it like a whole bunch of new points, and then we had them plot the predictions for all of these. And this also lets us see kind of the boundaries on which it separates the two classes, okay? And with a Gaussian Bayes classifier, it's actually a probabilistic one, okay? And so if you wanted to, so this is, again, the same kind of plot here. If you wanted to, you can give it, some x new value, and it will return back probability. So in this one, it was 89% class 0 and 11% class 1, okay? And some of these, it was 1, 0, 0, 1, like very clearly, but some of the other points were not as clear cut, definitely favoring one over the other. Okay. The author also does an example of multinomial Gaussian Bayes on classifying text, kind of using a bag of words model, which I'll just leave here and let you guys kind of read on your own time. And then some of the other things that he does. So he does naive Bayes, linear regression, which we've seen, and he also looks at support vector machines and random forests, which are also useful. Okay, all of these things. These are all kind of just machine learning things that you probably are covered in 101C, at least broadly, and then a little bit in 102B as well, right? So with support vector machines, this is kind of the two blobs he creates. And truly, all you have to do, so this is just kind of explaining what's going on and talking about maximizing margin. This is all actually unnecessary. Really, all you have to do is you do, from SVM, you have the support vector classifier, okay? And really, just like everything else, it's just model is equal to SVC. You can specify a kernel, okay? A linear kernel means a straight line boundary, and then you just do model is this, and then model.fit, okay? All of sklearn, it says, define the model, and then you do model.fit, and then for new points, you do model.predict, okay? All of this extra stuff over here is just so you can kind of visualize the boundary, but this is not actually necessary to do, okay? Really, the code just comes down to this. You define the model with some kind of kernel, and you do model.fit, and then now your model has been trained, okay? He writes all of this code here so we can see the actual margin and the boundary, which looks nice and is pretty, and we can start talking about what support vectors actually are, and it's these boundary points that define the boundary and stuff. But that's like for another class, right? So anyway, the thing about support vector machines is you don't have to have linear boundaries. You can use a kernel function. So if you have something where a straight line is not going to do a proper split, you can use a kernel function, which kind of, again, I'm not going to get into the explanation, but what it does is it projects the data into higher dimensions and allows for a linear boundary to be drawn there. But anyway, that code, all you have to do is you just change the argument from kernel linear to kernel RBF, which again doesn't really matter here, but basically you fit a support vector classifier, okay? And then again, he draws the boundaries for our own sake, but this was not actually necessary. The code, as far as sklearn goes, is just these two lines here. Define what kind of model you want to fit, and then you fit it, okay? And that's it, okay? There's a bunch of other stuff in this notebook which makes it nice and pretty. You can do things like soften the margin, which allows for misclassifications, okay? And again, the argument there is you now throw in this C. There's a cost function, okay, for how good or bad is it to misclassify a point, okay? And so if C is 10, it really dislikes misclassifying points. And if C is 0.1, it's okay with misclassifying points, and it allows things to kind of enter the border here, okay? So that's this is the one line that it uses for fitting a soft margin, okay? All of this other stuff is just kind of is used in the teaching example to show where the boundaries lie, okay? But then he does kind of an example where there's something called the faces in the wild data set, which comes from like 2007. So all the faces are like George Bush and Colin Powell and, you know, the world leaders in 2007, okay? And so so this is what we have. And you can use something like support vector. You can use support vector machines to help classify whose face is labeled, okay? And so these are, it's correctly labeling who's who based on these faces here, which is quite impressive. This is just an application of support vector machines without getting any more complicated, okay? And again, all of these things I strongly recommend if you're interested to read the notebooks and or textbook by Jake Van der Plas. I think the actual, let me see, Python, oh, I'm sorry, I'm going over my time. Python Data Science Handbook, I want to say the textbook is, is this it? Yeah, okay. So this page itself is the actual full text of the textbook as well, okay? And so you can read any of these things, and they're all kind of, they're pretty much just like his Jupyter notebooks, but they're all very very good, and it avoids getting into too much of the theory and stuff, which is a little, or algorithm, which is a little bit more reserved for 102B. But anyway, some of these examples I think are great. Could be useful for your modeling, maybe not. Okay, don't feel like you're pressured into using one of these things. Okay, we'll see you guys on Friday.